Okay, this is a proof of the fundamental theorem of calculus that I promised you guys this week that I'd get up for you. And here it is. So let's go over this document and give you kind of it's not a very rigorous formal proof, I would say. It's more of an argument. But it's going to suit our purposes here very well. So it's not as formal, but it is a demonstration of where this theorem comes from and how it works. So we start with a continuous function over an interval AB. So you have f being continuous over closed and bounded interval AB. So here's the f curve that you see. Now we're going to define another function here. We're going to define another function called g. Now g is the integral from a to x for that function. So what g does, g is actually thought of as sort of an area function. So if you can see here, this is the area in blue over the particular interval now from a to x. And x is a variable. A is fixed, a is constant. So this is going to give us the area under the curve f. And as you can see, g will be a nice continuous function as well, by the way. But we're going to find that area there, this g of x, from a to x. And that's how we define g in the upper left corner there. Now, what I'm going to do as well, though, since g is defined this way, I'm going to go to another location here, and maybe we'll color it, I don't know, purple. I'm going to add some distance h. And what I'm going to do now, this purple function, or this purple area that I'm going to describe now, this will be g of x plus h. And it's going to be from a to x plus h now, of that same function f of t dt. So just using this definition here on the upper left corner here, we can now create another function that's going to be more area, by the way, in purple. So I'm going to call that g of x plus h. So this is going to be, the purple area now, right? So if I can do something like that, I'll just leave it as is, I guess. And so in purple, this is what I'm describing as g of x plus h. Now, the reason I do this is because what I want to focus on now is this portion of the curve here. So I want you guys to focus on that middle portion in red here. Okay, because I'm going to define how we get that portion. This red portion. This is the area from x to x plus h. Now, what we can do now is we'll obtain the following rectangle by subtracting the two areas. Now, here's what I mean by that. What I could do to get that red area is simply the x plus h area in purple minus the g of x area. This is the difference here that I'm describing in red. Okay, so this is the area here. That's the difference. And when I do that, when I find that particular area, what I'll do is really focus on the approximating rectangle that we talked about here. There's an approximating rectangle there. So let me get rid of like the purple portion as a distraction and remark that we are looking at this red area in detail. And we also have this approximating rectangle there. And if we recall the approximating rectangle now as our focus, that's going to have dimensions, the height of which depending on the endpoint that you use, right? The height of which, if we use this left endpoint, the height of that approximating rectangle is f of x. And this distance h is the width. So what we're saying is that area is approximately that length of the approximating rectangle times the width, or that portion is going to be f of x times h. So I have this difference here going to be approximately f of x times h, and this is what this is where I'm at here in the portion there. These are approximate. And this is what we're describing. We obtained the following approximating rectangle by subtracting two areas. This is the g of x plus h minus g of x, which is approximately h times f of x. Now this implies, ladies and gentlemen, if I divide both sides by h, this implies that the function f itself is approximately the difference there. And it's a difference quotient, by the way, g of x plus h minus g of x over h. That's going to be what our function f is. So we have an approximation for the f function. Now, this is a really crude approximation. And this is the picture of what we're describing here. And it's really the red portion here now. If we want to change colors, that's fine. But this is the blue approximating rectangle for what we're talking about there. It's a very bad approximation if we try to do it that way. Anyway, here's the thing. As we obtain better and better approximations by letting this h go to 0, now this is a limit here. We let h go to 0. We obtain the following relationship, that the function f now is no longer here based on this relationship. F is that difference quotient. The function f is no longer an approximation there. That area is no longer an approximation. It's actually an exact area. And this is the limit that we're talking about as h goes to infinity. Now, as h goes to infinity, what you notice is we have shown that the function f is really g prime x. So f is really g prime x. Now, what that means is, specifically, since f is g prime x right up in here, we say g is the antiderivative for the function f. That's the definition of the antiderivative. But the more general definition of the antiderivative is g of x plus c. And this is what we're saying right in here. So this is kind of the essence of the fundamental theorem of calculus part 1. It's the essence of it. And I summarized it right in here. So here's the summary. That f is a continuous function over an interval ab, closed and bounded interval, where g is defined this way. As the integral from a to x f of t dt, it's continuous over that same interval, and it's differentiable over the open interval ab. Then f here is equal to g prime x. And that's what we just showed. Or we really specifically showed that this statement here, that g is the antiderivative of f, because if you recall here the definition, of antiderivative, this is what we're saying. Moreover, we have the general version of this, which is g of x plus c, which is f of x. That's a fundamental theorem of calculus part 1. Now, part 2 essentially says, well, what is, in fact, this g? Well, we know what g is. It's an antiderivative. So we replace that definition here with the antiderivative big F for that g. You know, that's all the fundamental theorem of calculus part 2 comes in and starts to discuss. So I started to say to you, take a look at this theorem here. What I'm going to prove to you is the part 2 portion here. But this is where we start to talk about this relationship between g and this antiderivative. Now, this is because of the following. Now, since we know how g is defined here, right? G is defined as the integral from a to x of f. And we know the definition of antiderivative. This is everything that I just spoke about here, here, specifically here. And it's the antiderivative for f. Okay, we're going to put these ideas together now. We're going to kind of show you the great detail for the Fundamental Theorem of Calculus Part 2. Now, if I look at g of a, if I use my definition of g, and I plug in the value a, what you're seeing here now, ladies and gentlemen, is the area under a point. Because the lower limit is a, and the upper limit is a. So if I just use that definition and I ask, well, what is this area? Well, the area under the curve at a point is 0. It's negligible because there is no width for a dimensionless point. Now, what they mean by dimensionless is simply the statement here. There's no width. There's no approximating rectangle. You have a length, but you don't have a width. The width is 0. And so if the width is 0 there, then the area is 0. It's negligible. So the area under a curve at a point is actually 0. And this is what we're referring to in this picture. And that's going to be important for us. Because now what I'm going to do is this. We're going to plug in these values we're going to find what this difference actually is, this f of b minus f of a. We're going to plug in the values now. By definition, this is g of b plus c minus g of a plus c. And doing some arithmetic, because c is that same constant, we simply get gb minus g of a, or I should say algebra. You know, we are going to distribute this negative sign here. You guys know what I'm talking about. And what you now end up with, since g of a portion here, we noticed already was 0, it's negligible. F of b minus f of a is this g of b here. So this is how we know now f of b minus f of a is equal to the integral from a to b f of x dx. This is the conclusion of the Fundamental Theorem of Calculus here. Okay, since remember the definition of g here of b is the integral from now a to b, that f of t dt, or even f of x dx, it doesn't matter here because the variable can be either x or t. We actually change it on you in version 2 here. Doesn't matter what the interval it's called. That's why you see you went from t to x. But what we're sharing here with you is that this portion here is this f of b minus f of a, and that's the Fundamental Theorem of Calculus Part 2 here. So this is what we've been using all along. We simply write it this way, though, that if we want to integrate from a to b to find that area under the curve over the interval ab, it's really the antiderivative of f evaluated at the endpoints. And remember the notation that we often use here is we say, here's my f of x, lower limit x is a, upper limit x is b. Now, ladies and gentlemen, here you go. Here's that video I promised you on the proof of the Fundamental Theorem of Calculus. It's not a rigorous proof. It's not the most formal proof. It's somewhat of an argument. But anyway, this kind of gives you an idea of what you're using and why you're using it. So I wanted to get this out for you guys, this weekend, like I promised. So thank you so much. I hope you enjoyed the demonstration, and take care.